Good morning, everyone. I'm recently I am the PhD student in Delhi University of Technology. Today I am going to present here my work that was done in Department of Material Science, Delhi University of Technology, under the supervision of Sorry Beresby. And the title of my work is Physical Vapor Deposition of N-copper indium-3 selenium-5 photoabsorber films for hybrid polymer solar cells. It means that my topic will discuss the copper indium-3 selenium-5, a group of copper indium selenium compound for the photoabsorber layer, not the complete solar cell. Before going to the actual talk and my work in this topic, I would like to introduce what is copper indium selenium group of compounds. Copper indium selenium photoabsorbers are under serious investigation as a prospective material for solar cell. As you know that in Delhi University of Technology, in Department of Material Science, most of the research are going to be done on either in CISC or CZTS compounds, and in our group we are concentrated on copper indium-3 selenium-5 and copper indium-5 selenium-8. Here, why we are going to do this investigation in copper indium selenium group of compounds? Because these materials are very high optical absorption coefficient of more than 10 ppm per cm, easily adjustable band gap, high stability, and easy N and P type probability. The another thing is that the copper indium-3 selenium-5 is considered as a order vacancy compound with a band gap of 1.3 electron volt, which is close to the solar spectrum. And the next thing is that what are the potential application of the copper indium-3 selenium-5 photoabsorbers in hybrid field structures depends on the properties and quality of prepared films. Example, compositional uniformity, crystal structure, doping density, charge carrier profiles, etc. And also our the way what are our objective? What is the objective of our research? The objective of our research is that we want to develop N type of copper indium-3 selenium-5 photoabsorber films, so that in the next step we can put P type of any organic material in order to make the complete hybrid solar cell. And also the next objective of our research is that we want to find the optimal deposition and post-treatment parameters for CISC photoabsorber layers prepared by high vacuum evaporation. It means that the annealing condition or the deposition, and after deposition the heat treatment temperatures will affect the performance of the photoabsorber layers. So our objective is to find optimal deposition and post-treatment parameters for CISC photoabsorber layers prepared by SB. Now I am going to show the slides how we used to prepare the CISC materials. In this case, this is the device where we will deposit the copper indium-3 selenium-5 thin films by compound copper indium-3 selenium-5. For this, we use glass ITO and glass substrates, which were cleaned ultrasonically and by using Nova scan ESD ozone cleaning system. After cleaning this, we have taken around 0.6 gram of compound copper indium-3 selenium-5, which was put here, and this glass ITO and glass were put in the rotating disc here, and after the temperature of the rotating disc was taken at 200 degrees centigrade, and the compound copper indium-3 selenium-5 raw material was deposited at a rate of 0.95 nanometer per second, and the complete film of as deposited around 200 degrees centigrade was found which thickness was around 400 nanometer. The ice deposition vacuum, the pressure was around 10 to the power -6 millibar, and after after depositing as deposited material, it was taken outside, and to find the optimal deposition, optimal costing treatment parameter, we applied enabling condition for around 300 degree centigrade, 350, 400 degree centigrade, 450, and so on up to 500 degree centigrade. And also for our past in our laboratory, we have experience of doing double annealing, and therefore we also applied double annealing in argon and again in for 4 hours step by step. Then the prepared structures, thin films, were studied by using HRSM, XRD, Raman, UVIS, ID, and impedance spectroscopy. Now I am going to show the results of our structures. This is the scanning electron microscope pictures of the developed films. As the film were developed in glass ITO, and there is a glass ITO, and then the copper indium 3 selenium 5 thin films. But these are the cross-sectional images of the films. The films shows that this is the ITO layer, thereafter there is copper indium 3 selenium 5. But this is the as deposited temperature around 200 degrees centigrade. Therefore, the deposited material is not completely homogeneous. It means that we can see here clearly the two layers. One is this, another is this. The composition of the within the composition of the layer is the HRSM image of as deposited CIC shows two layers. The top layer is copper indium diselenide, and another is the middle one is highly indium rich. But the overall composition of the layer is copper indium 3 selenium 5. Then we go on increasing the temperature from 200 degrees centigrade to 500 degrees centigrade. After increasing the temperature to 300 degrees centigrade for 1 hour, the crystal structure doesn't change enormously. But when we go on increasing the temperature up to 450, the structure goes on increasing, but still we can see two layers. Then we increase the temperature up to 500 degrees centigrade, 480 for 2 hours, 500 degrees centigrade, and also double annealing layer. If we increase the temperature, the crystal size increases, and again at 500 degrees centigrade for 4 hours, the structure is homogeneous, and we conclude that according to the HRSM image, our structure was double annealed as 400 degrees centigrade at 400 degrees centigrade in argon and vacuum. So the best structures as the grain size is increased. In this case, the grain boundary gets reduced. And we also analyze for this temperature by using the EDS analysis. For this, we can see from this picture that whether our sample is stoichiometric or not. We need this because we have our source polycrystalline is nearly copper indium 3 selenium 5. It means that our source polycrystalline source copper indium 3 selenium 5 is copper indium 3 selenium 5 in structure. When we for the as deposited material, the stoichiometrical ratio is diverse. It means that it is copper indium 2.6 selenium 5 nearly. When we go on increasing the temperature from 300 degrees centigrade to 500 degrees centigrade, we again go nearly to the stoichiometrical ratio of copper indium 3 selenium 5, but not exactly the 3. And we also did the XRD of the copper indium 3 of the previous CISC layers. From this graph, we can see that this is the ITO in ABCDE. This goes on increasing from 300 degrees centigrade to 500 degrees centigrade for 4 hours. When the temperature goes on increasing, this peak, which is 1123, goes on increasing. It means that at higher temperature, the recrystallization of the copper indium 3 selenium 5 phase goes on increasing, which we actually want. From this, we can conclude that the prepared CISC layer is chalcopyrite in structures, and with the increasing of the temperature, the recrystallization of the copper indium 3 selenium phase goes on increasing. Similarly, these studies were also confirmed by doing Raman spectroscopy. From this Raman spectroscopy, we can see that as the temperature goes on increasing from 300 degrees centigrade to 500 degrees centigrade for 4 hours, 300, 450, 480, 500 degrees centigrade, this speed also goes on increasing. This is 300, 450, 480, 500. It means that the peak corresponding to, this is the surface Raman spectrum. The peak corresponding to 175 goes on increasing, which is copper indium diselenide. And we can also see some trace amount of the copper indium 3 selenium 5 around 152 per cm, and also some copper selenide and indium selenide at 95 and 130 selenium 130. And we conclude that the surface Raman conclude that the prepared structure in the surface is not purely in copper indium 3 selenium 5, but is the mixture of the phases. Similarly, we also use the Raman spectrum for double ended structure. Copper indium 3 selenium 5 for ended in argon and vacuum at 500 degrees centigrade for 4 hours. And this spectrum we have taken at 2 different places the Raman spectrum, which coincides, and the result is that the surface Raman of the 500 degrees centigrade double ended structure shows that one peak at 174 per cm and 152 per cm. According to the literature, this peak can be associated with copper indium 3 selenium 5 or copper indium diselenide. And also we can see the 152 per cm, which is copper indium 3 selenium 5. Similarly, we have also drawn the Raman spectrum of the cross section of the prepared sample. The peak of 152 per cm corresponding to copper indium 3 selenium 5 goes on increasing as the annealing temperature goes on increasing. The annealing temperature, if we see this graph from here, the annealing temperature goes on increasing from 300 degrees centigrade to 500 degrees centigrade, and the phase of the copper indium 3 selenium 5 also goes on increasing. But still we can conclude that the prepared CIAC film at 500 degrees centigrade for 4 hours is a mixture of the phases. Similarly, this is the concluding graph of the Raman spectrum with surface and cross section. In the surface, copper indium diselenide is a dominating phase, and in the cross section, copper indium 3 selenium 5 is also one of the prominent phase with copper indium 3 selenium 5 phases. And next, we also did the current voltage characteristics of the glass ideal CIAC, and we use graphite dot as another contact. And I am telling that we are going to investigate the copper indium 3 selenium 5 as a photo observer material only. It is not a complex solar cell. Therefore, this graph is taken as with ITO and copper indium 3 selenium 5 and graphite structure. Here, from this graph, we can see that the current voltage characteristics of this graph shows the non-linear relationship between current and voltage. From this, we can conclude that as the temperature goes on increasing from 450 degrees centigrade to 500 degrees centigrade, the non-linearity of the relationship between this and this goes on increasing. It means that it acts as a diode, p-n junction diode, and we can also tell that the barrier, there is a presence of such barrier between CIAC and ITO, or metal and semiconductor. If we see the photosensitivity or the reading photosensitivity of the prepared sample, as the temperature goes on increasing from 450 to 500 degrees centigrade, the difference between the dark current and the light current goes on increasing. It means that the photosensitivity goes on increasing as the annealing temperature goes on increasing. Or either we also can say in another way that if this dark current, if we measure only the dark current and the light current, this portion will be the dark current and another will be the light current. Therefore, if we see the change between dark and light current, the relative photosensitivity goes on increasing. And from this graph, we can conclude that the copper CIAC layers ended at 500 degrees centigrade for 4 hours shows the highest photosensitivity. Similarly, we also did this by using photoelectrochemical method, and the relationship between current and voltage is non-linear in characteristics and the highest relative photosensitivity at 500 degree centigrade for 4 hours. And we split the graph in two parts of 500 degree centigrade 4 hours in vacuum, argon and double layer. And the maximum difference between the light and dark current is observed in 500 degree centigrade for 4 hours in double layer. Similarly, this is the graph of the Nipist plot, which shows that a single semicircle and the presence of there is a single barrier between the ITO and the CIACDS. Similarly, from UPS spectroscopy, we calculate the charge carrier concentration of the treated structures, which is around 4 into 10 to the power 17 to 7 into 10 to the power 17, which is appropriate for the solar cell structures. Finally, I would like to conclude my talk. CIAC photo observer layers with overall composition close to copper indium 3 selenium 5, which we see from the EDS analysis, were prepared by using high vacuum evaporation technique, with following annealing in vacuum and also double annealing with pure argon and high vacuum. The X-ray spectrum shows the calcopyrite structures of HPS and NMCIAC layers. Similarly, annealing in vacuum induces the polycrystalline structure and TB properties of deposited CIAC layers. Maximum content of copper indium 3 selenium 5 was found in CIAC layers annealing in vacuum at 500 degree centigrade for 4 hours, and dominating phase of copper indium 3 selenium 5 was also observed in double annealing in argon and vacuum at 500 degree centigrade for 4 hours. It was found that the CIAC double annealing in 500 degree centigrade for 4 hours has the maximum photosensitivity and the charge carrier profiles were calculated from the impedance spectroscopy were suitable for the solar cell application. And we conclude that these structures can be in the future can be applied as an N-type photoabsorber in the N-type photoabsorber with P-type material in order to make the complete solar cell. Finally, we are grateful for the financial support from the Union Ministry of Education. And thank you.
Thank you. You missed the greatest sense of the doctor of school. Okay, question, please.
Yeah, this whole talk is also available in Springer link and
Question, Madam.
I have a question. You didn't say how thick is your film at all. So, because you showed that there were Raman spectra of the cross-section, what does it mean you didn't introduce that? You took the Raman spectra from the cross-sectional Raman spectra. For me, it's not clear what you made.
Yeah, this is the cross-sectional Raman spectrum of 400 nanometer. But I understood because it is the average grating size which we get that one.
Okay. And I have a second question. The copper indium selenide is the best known absorber layer. Now you are going to the another compound, what is N-type. Can you compare these materials? Why you are so interested in this vacancy order compound?
Yeah. Copper indium diselenide is highly researched and it is researched everywhere, and maybe further in order to do new research in copper indium 3 selenium 5 or group of compound, we are not interested in copper indium diselenide. Yeah. Because this is copper indium diselenide is researched everywhere, and so copper indium 3 selenium 5, copper indium 5 selenium 8, other compounds are not researched. Therefore, we want to research in this compound. This is only one of the possibility only.
You believe that it will be much more better absorber?
Yeah.
Okay, that's great. I have another question, additional one. you have mixture of phases,
Yeah.
huge amount of another phases.
Yeah.
And
Yeah,
it will be nice if you will characterize which one of those additional ones is killing for your so-so. Or maybe somebody from this family is useful. Please.
That is the limitation of our research because we want to demobilize all phases and achieve only copper indium 3 selenium 5, copper indium 3 selenium 5 flip or copper indium 5 selenium 8 flips, which is blocking up further steps also because we are not able to do PL spectra of these flips as we are not getting copper indium 3 selenium 5 or copper indium 5 selenium 8 pure phase. We will do other annealing or other technique in order to introduce only copper indium 3 selenium 5 or copper indium 5 selenium 8. We don't want that other copper indium dicyanide or other phase in our compound, in our structure.
Thank you. Yeah, please.
You made a Raman spectrum starting from 40 wavelengths. Which kind of setup you use and what was the excitation source of laser? But you don't make a Raman spectrum.
Yeah, can you repeat your question once?
Which kind of Raman setup you use? What was the wavelengths of laser what operates this setup?
This is the x-axis. This is the x-axis, which is the energy from 60 per cm to 260 per cm by using HR. This is the x-axis of the Raman set, and this is the intensity.
Okay, I understand. What was the setup? Company who produced the Raman setup?
Okay, I understood you mean the name of the device that was used in the Raman spectrum. Yeah.
Yeah, okay, thank you. Läheme siis edasi. Ja Helena